Hello. This lecture will cover pages 23 through 24 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on resistive circuits, Chapter 2B, Kirchhoff's voltage law. We're going to start out on page 23. And the last lecture we talked in detail about Kirchhoff's current law, and now we're going to look at a second law that's very important in engineering called Kirchhoff's voltage law, KVL. KVL states that in any complete electric circuit, the algebraic sum of the EMFs, the voltage rises, must equal the algebraic sum of the voltage drops. So in an equation form, the summation around any closed loop of the voltage rises must equal the summation around the closed loop of all the voltage drops. Or we can say the algebraic sum of the voltages around any closed loop have to be equal to 0. The algebraic sum around any closed loop with n elements has to equal 0. Where n here represents the number of voltage rises and drops in the closed loops. It's a number of elements you have to deal with. So let's take a look at what KVL tells us. We have a simple series circuit here. Notice you have a source of EMF E, and we have 3 resistors here, and I'm showing current flowing through the circuit in a clockwise direction. I just showed it as a loop current here, I. Notice I'm putting the passive convention in. Very important you put the passive convention in, plus to minus, and plus to minus as current flows through the elements. The voltage across resistor R1 is V1, the voltage across resistor R2 is V2, and the voltage across resistor R3 is going to be V3. Make sure you use the passive sign convention as we discussed in the first chapter. Clockwise around loop 1, starting at the lower left corner by KVL. We're always going to start at the bottom left-hand corner of every window. That's just nice convention. It allows me to give you partial credit on your problems. So whatever window you're working in, and you'll see what I mean when we start working on the circuits, always pick the bottom left corner and start going around in a clockwise direction. So we're starting here at a 0 voltage reference, and we're up plus E. Minus to plus, that's a rise. Plus E minus V1, it's a drop, plus to minus. Minus V2, minus V3, and we're back to the ground reference. This is all the same point. So there's our first KVL equation. On page number 24, another example. For the circuit below, use KVL to find the voltage across R3. This is a example 2.9 in the book, but we're going to use my convention here. You could look over the author's solution, very similar to mine, except he uses the opposite sign convention. So here's the circuit. We're going to find VR3 to Kirchhoff's voltage law. The sum of the voltages around any closed loop, the algebraic sum of the voltages around any closed loop has to be equal to 0. So I write around loop 1 by KVL. Not KCL, we're doing KVL. So I start down here at the bottom left-hand corner and I go around that loop. Plus 30, it's a rise. Minus 18, that's given. Plus the minus. Plus 5, it's a rise. Minus 12, it was given. Plus 15, it's a rise. Minus VR3, that's the voltage across resistor R3. Minus VR3 equals 0. There's our equation. There's our linear equation. Solving it for R3, R3 is equal to 20 volts. There's examples in the book and there's learning assessment problems. We're going to look at each one of these before you can start the homework. So starting out in the book, let's take a look at example 210. You can find that in the textbook. But it says consider this network. This network really has 3 loops you can go around. You can pick the left loop, You can pick the right loop, or you can pick the entire loop here. You can extract all the useful information that you need when we start doing our loop equations by making sure you cover all the elements. So what do I mean by that? If you pick a loop here on this left window and a loop on the right window, the loops went through every element. Okay? But what if we pick just the outer loop? We go around this loop right here. You could do that. And then you need a second equation to pick up these elements. Well, it's either this loop or this loop. You don't need both of them. You don't need three equations, and that's what they're explaining here. So let's take a look, and let's just go around the left loop here. Let's start at this bottom corner, and let's go around this loop, and let's see if you get this equation that the author got. Well, I want you to go ahead and do that right now. Stop the video and go around that loop, and just refer to this as VR1, and this is VR4. And let's see what you get. I'm going to do the same thing. Grab a piece of paper here. And let me just write the equation real quick. I'm going to start down here, and we're going to say a plus 24 minus VR1 minus VR4 plus 16 equals 0. And if you look at that equation and you compare it to the one the author got down here, you're going to see that it's the negative. The same information is there. He gets a negative 24. He gets a plus and a plus here. And he gets a negative 16. But this is the equation you'd end up with in my class. I want you to go ahead and do it on the right loop here. Start down here at point F and go around and see if you get basically this equation and he gets down here in the book. We're just setting you up for the next chapter here. Let's take a look at 211. Here's problem 211. It's a good problem because it shows you that you don't need to pick a loop that includes all the elements in the circuit to find a particular voltage. In other words, here they want you to find voltage VAE. They want you to find the voltage between this point here, VA, and VE. And it spans multiple elements. Well, you can do a loop. You can start at this corner and go around and just refer to that as you can just jump from here to here. That's a closed loop. It's a closed loop that takes into account from point A to point B because we're calling that point A to point E. We're calling that VAE. And notice our convention here that we talked about in the first chapter. When you say VAE, that is essentially VA minus VE. You're assuming A is the positive most point. So you have to put a plus on this side. And you have to put a minus down here when you refer to this voltage as VAE. Let's go around the loop here. If we go around this loop here, starting at this point, what are we going to end up with? We're going to end up with plus 24. We're going to end up with a minus VAE. And we're going to end up with a minus 10, and that's equal to 0. So I want you to take a look and see if you get this equation right here. How am I getting this equation? I'm starting at this point, and I'm going around this loop. And I'm referring to the open voltage here as VAE with A being positive and E being minus because of the convention here. And notice it's exact same equation that they got down here. It's the negative of the equation, but it's the same information. Because you can multiply negative 1 by both sides. If you multiply this side of this equation by a negative 1 and the 0 by minus 1, you get the same information. I want you to go ahead and see if you can write an equation using VAE. Let's see what else they wanted here. They wanted VEC. VEC. VEC is this voltage here, VEC. With E being the positive and C being the negative. See if you can get the information they got down here at the bottom. Let's take a look at 212. Example 212, right here in the book. They want you to come up with two equations. One equation using the left window, using Kirchhoff's voltage law, and one equation on the right window, using Kirchhoff's voltage law. What I'd like you to do when you work out my solutions is to say around loop 1, call that loop 1, call that loop 2. These aren't nodes now, we're doing loops when you do voltage law. So the Kirchhoff's voltage law, you're going to say around loop 1 by Kirchhoff's voltage law. And you start down here and you write the voltages around. And you're going to get this equation. The negative of that equation. You're going to get a plus Vs, a minus VR1, and a minus VR2 equals 0. Then you're going to say around loop 2 by Kirchhoff's voltage law. And you're going to start at point D and you're going to go around here. And you're going to call this a plus VR2 minus 20 VR1 minus VR3 equals 0. You're going to get the negative of that equation. So what you're going to end up with is two Kirchhoff's voltage law equations. We're going to look at the learning assessment problems now real quick. Each one of these. E27, we're going to look at E28 and E29. What I'd like you to do is get a piece of paper. And E27 is Kirchhoff's current law. It's a current law equation. I want you to go ahead and I want you to try to work that problem. Try to work each one of these three problems real quick, and then I'm going to go over them, give you a solution. It'll be a nice preface before you try the homework. If you can do these, it'll help a lot. Let's start out at 2.7. How'd I get 2.7? Well, in 2.7, you know, I treated this as a surface. We're going to refer to this as a super node when we get to chapter 4, but in any event, just treat this as a black box. This is some part of the circuit here, and you have to find IX before you can find I1, or you'll run into problems, difficulty here. So just treat this as a black box. Just treat this as one big node. It's really not a common node because there's a resistor in here. But currents flowing into this cloud have to be currents flowing out of the cloud. So I called this an area, area A. And I said, at area A, by Kirchhoff's current law, well, I have minus Ix, it's coming out of that cloud. And I have a plus 6 milliamps going in. And I have a minus 1 milliamp coming out of the cloud over here. And I have a minus 1.5 Ix. That's a current controlled current source. That's a dependent source, but it's coming out. Equals 0. You solve that for Ix. Ix has to be 2 milliamps. Now, if you know Ix being 2 milliamps, you can solve for I1 and go back to just this particular node. We don't have to worry about an area anymore. At node B, by Kirchhoff's current law, minus Ix plus 6 milliamps minus I1 equals 0. I1 is 4 milliamps. Finished. Problem 2.7 or 2.8. If you look at problem 2.8, it's similar to one of the examples I showed you. We're going to use Kirchhoff's voltage law to find VAD and VEB. Don't forget, A is going to be the plus and D is minus. E is going to be plus and B is minus. The convention we talked about in chapter 1. So my first loop is going to be here. It's not going to be the outer loop, this whole loop. It's going to be a loop that starts at F, goes up to A, and shoots down to E. It's going to be this. It's going to go A. We want AD. So my loop's going to go from F to A to D. It's going to be this. Here's my loop. I'm going to call that loop 1 right there. I can form any closed loop I want. It doesn't have to have one element in it. So I'm going to start down here and I get plus 6 minus VAD, the unknown. Why is it a minus? Because it's plus to minus. VAD, A must be positive and D must be negative. Plus 12 plus 8 equals 0. VAD 26 volts. Around loop 2, they want to find VEB. They twisted these letters around. a little bit for you to see if you can handle that. Well, I think you can. Obviously, the author couldn't. The answer's wrong in the book here on the solution for this. But VEB, that makes E positive with respect to B. So I'm going to start here and go around, and this is my loop right here. Whoops, I'm sorry. This is my loop right here, with E being the positive and B being the negative. It's a drop. Why is E positive? Well, because we're finding VEB. That's what we need to find, and E is the positive. It's the first letter represented. It's the most positive. So we start here, and we go VEB. Oh, let's take a look at this. The author did that right, and I made a mistake here. I made a mistake when I was working this out, and I'm glad I did, because it's easy to make these mistakes. E's being the most positive. So if I go around this loop and I go from E to B, I'm dropping. This should be a negative sign. That should be a negative. Minus VEB, minus plus 4, minus 6, plus 12, and we're back to that point again. Okay, and if you solve this, you get a plus 10 volts. You get a plus 10 volts. The author was right. And then finally, I'll do one more problem here real quick. I wasn't going to assign this one, but you know what? As much as I can give you, it helps you out. There's this problem here. I don't know if you can see it. I'll hold it up. It's problem E29, wherever it is in your book. They want you to find VBD. And I made an outer loop. I had to do an outer loop first so I could find VR1. I had to do the whole main loop there. And I found VR1 is 1 volt in my solution right there. And then I made my own loop. I called it loop 1. And I used Kirchhoff's voltage law around that loop. And I used the VR1 I found in the first equation. And I ended up with VBD equal 11 volts. So now for the next 3 or 4 weeks, matter of fact, through the next maybe 6 weeks, we're going to use Kirchhoff's voltage law, and we're going to use Kirchhoff's current laws. We're going to use both of those laws. And you're going to see how useful they are. We went through the basics. Make sure you understand the basics of the law. You'll be just fine. That concludes this lecture.